So now we've talked about an overview of cellular respiration, let's go over each of the 4 steps in detail to figure out how do we make these 32 to 36 ATP starting with glucose. So just to revise the first steps of cellular respiration in the first video, glycolysis splits glucose into 2 molecules of pyruvate. And that releases a tiny bit of ATP, just 2. Now in pyruvate oxidation, what we now do is we make high energy electron carriers, just a few, but we're going to make a few high energy electron carriers. And then the Krebs cycle, what happens now is that the products of pyruvate oxidation are going to go into the Krebs cycle, and we're going to fully oxidize what's left over of glucose. Now, oxidation means a loss of electrons. We'll explain that as we go through this video. So these first steps, glycolysis, pyruvate oxidation, and the Krebs cycle, the goal of those is to make high energy electron carriers. And we'll talk about those on shortly. Now those high energy carriers are now basically the energy contained in a glucose molecule. It's now been transferred to these high energy electron carriers. So the energy is now used to make the majority of ATP in the electron transport chain, which is the final step. So the first 3 steps, glycolysis, pyruvate oxidation, and the Krebs cycle, are basically harvesting the energy from glucose, and then that energy is used to make loads of ATP. So the vast majority of this ATP here comes from this final step. Before we start talking in detail about the different steps of cellular respiration, let's talk about some important molecules that are involved. So ATP is energy that's used by cells. We can't use glucose directly, we need to make ATP. And the way we make ATP is by creating a high energy bond between an ADP molecule and a phosphate. So ATP is an adenosine molecule and then 3 phosphate molecules. And this bond here, this bond between the 2nd and the 3rd phosphate, has loads of energy in it, and we can break this bond to release that energy. And the reason why we need glucose to make ATP is that if we want to make a high energy bond, we need to put some energy in, and the energy we're going to use is from glucose. Another important molecule is NAD+, and what we do with NAD+ is we add electrons and also some hydrogens or some protons at the same time to make NADH. And there are lots of energy within electrons, and so when we make NADH by putting electrons onto NAD+, we've made a high energy molecule, and it's that molecule that we use to power the process of making ATP. So this is called a high energy electron carrier. And we'll be talking about that in all of the steps of cellular respiration. Now FAD is very similar to NADH in the sense that we can add some electrons to it to make FADH2, and that's also a high energy electron carrier. So we're going to produce that in the Krebs cycle, just a few of them. The main molecule we're talking about when we talk about high energy electron carriers is NADH. Another thing we need to think about is redox reactions. Now, redox reaction stands for reduction and oxidation. So when we are making our high energy electron carriers, we are adding electrons to them. So if we reduce something, we are gaining electrons. When we oxidize something, That's loss of electrons. So what we're going to do is we are going to oxidize glucose, take the electrons from it and reduce NAD plus and FAD to make these high energy electron carriers. The way you can remember is with the term oil rig. Oxidation is loss of electrons, reduction is gain. So, the 4 steps of cellular respiration in detail. The first step is glycolysis. And what glycolysis means is lysing, which means splitting. Glyco refers to glucose. So we are going to split glucose. And we're going to split glucose into 2 pyruvate molecules. Okay, so what we're doing here is we are taking a 6-carbon molecule, which is glucose, and we're going to split that into 2 times 3 carbon molecules. So 1, 2, 3, 1, 2, 3. Each one of these is a 3-carbon pyruvate molecule. So all of the steps that we're going to do from this point onwards, that we're going to apply to 1 pyruvate molecule, we're going to do twice per glucose molecule. Now there are 2 steps of glycolysis. The first one is an energy investment stage. And here we are going to use 2 ATP molecules. Okay, so right now let's keep track over here of how many ATP molecules. We've got -2, so we've used 2 ATP molecules, and this is per glucose molecule. Now the second step is an energy harvesting phase. And this is going to create or produce 4 ATP molecules. Okay, so now we've got plus 4 ATP molecules. So overall, glycolysis is going to produce 2 ATP. And we say this is net ATP. So net ATP refers to accounting for the ones that are used and the ones that are produced. So these pyruvate molecules are now going to go to the second step of cellular respiration, which is pyruvate oxidation. So in this second step, we are going to oxidize the 2 pyruvate molecules. And if we remember the term oil rig, remember that oxidation is a loss of electrons. So we're going to take the electrons from pyruvate, or some of them. Now, remember that the goal of the first 3 steps of cellular respiration is to make high energy electron carriers. So those electrons are going to be put onto NAD plus to make NADH. So here's our pyruvate molecule, and we are going to oxidize that into a molecule with 2 carbons called acetyl CoA. Okay, and in that step, you see we've got 2 carbons here. We started off with 3. 1 carbon is going to be released as carbon dioxide. So this step here, the release of carbon dioxide, some of it comes from the second step, which is pyruvate oxidation. We're going to release just 1 carbon dioxide per pyruvate molecule. So from the 6 molecules of carbon, the 6 atoms of carbon that were in our glucose molecule, we've released 2, 1 per pyruvate molecule. Okay. In the process, we are also going to make NADH. Okay, remember we have oxidized pyruvate. Oxidation is loss of electrons. We're going to put those electrons onto NAD plus to make NADH, a high energy electron carrier. So the products of pyruvate oxidation are, per glucose molecule, 2 molecules of carbon dioxide and some NADH. That NADH is going to go into the last step, which is the electron transport chain. This carbon dioxide is exhaled. This acetyl-CoA, 2 per glucose molecule, are going to enter step 3, which is the Krebs cycle. So on to step 3, the Krebs cycle. Before we talk about the Krebs cycle and what it is, let's just see where we are with our original glucose molecule. So here is our glucose molecule that has 6 carbons in it. That was split into 2 molecules of pyruvate in glycolysis. Remember, glycolysis means splitting of sugar. Then we went through pyruvate oxidation in the 3rd step, and we produced 2 molecules of acetyl-CoA. Now notice that those are 2 carbon molecules, so 1 molecule of carbon per pyruvate, 1 atom of carbon, was released into a molecule of carbon dioxide. So we've got 2 carbon dioxides that have been released here. So of our original 6 carbon atoms here, we now have 4 left. 2 have been released as carbon dioxide. Now we're going to enter the Krebs cycle. And the Krebs cycle is a cycle, as the name suggests, and cycles are used in biology by living things because they are much more efficient than building or breaking down molecules completely. To build, for example, a glucose molecule from scratch is a lot harder than incorporating some carbon, for example, into a biological molecule that already exists, and that's what photosynthesis does. That also uses a cycle. So what we're going to do in this cycle is we're going to start with a 4-carbon molecule of oxaloacetate. This is a biological molecule. And we're going to take 1 of these acetyl-CoA molecules that came originally from our glucose, then to pyruvate, oxidized into acetyl-CoA, and we're going to add those here onto our oxaloacetate molecule. So we now have a 6-carbon molecule. Now what we're going to do is we're going to fully oxidize the acetyl-CoA and return back through a series of steps, there are molecules along this way, back to our oxaloacetate. Now remember, oil rig, oxidation is loss of electrons. In that process, 2 carbons are going to be released as carbon dioxide. Okay, so we've got 2 carbons coming off here as carbon dioxide as we take the electrons off. And the electrons are going to go onto NAD plus to make NADH, our high energy electron carrier. We're also going to make some FADH2, which again is a high energy electron carrier. So what we've done is we've taken the electrons from this molecule of acetyl-CoA and we've put those electrons onto FAD and NAD plus to make these high energy electron carriers, which we're going to use now to make ATP in the final step. So of our original glucose molecule, now all of the carbon atoms have gone. 2 were released in pyruvate oxidation and 2 per acetyl-CoA were released in the Krebs cycle. There are 2 molecules of acetyl-CoA, that means 4 carbon atoms, so that makes our 6 carbon atoms altogether have now been released. So in steps 1 to 3, we are going to fully oxidize glucose, and those electrons are going to go onto high energy electron carriers, and we're going to use those in the last step. So overall, in the Krebs cycle, we are going to make 8 NADH, 2 FADH2, 2 ATP, and 4 CO2, and this is per glucose. So ask yourself, how many times does the Krebs cycle need to run per glucose molecule? Well, for each glucose molecule, we've got 2 molecules of acetyl-CoA. The cycle runs once per molecule of acetyl-CoA. So this one's going to go first, and then this one's going to go. So it's 2 times. 2 Krebs cycles per glucose molecule to create this. So the final step is the electron transport chain, also referred to as the ETC. So where we are now in the whole process of cellular respiration is we have fully broken down, fully oxidized our glucose. So glucose is now gone, and our carbon dioxide has been released. We've made a little bit of ATP, but nothing really to write home about. So the electron transport chain is where we see the oxygen, the water, and the majority of the ATP, those parts of the equations. And remember that the goal of the first 3 steps, what the point of those were to produce high energy electron carriers. So NADH was produced in the first 3 steps. So what we're going to do now is we're going to bring our NADH and our FADH2, which is also a high energy electron carrier, and those are going to donate their electrons to this process. So we're going to take the electrons off NADH to make NAD plus, and FADH2 to make FAD. And those electrons are going to be used to power the movement of some protons across this membrane. Okay, and that all sounds like complete gibberish, but stick with me, you'll see what I'm talking about. So this here is the membrane of the mitochondria, the inner membrane of the mitochondria. And these blobs here, these are proteins. And one of these proteins is ATP synthase. And ATP synthase, as its name suggests, makes ATP. Now the rest of these are involved with moving electrons. And what we're going to do is we're going to move an electron through, there's another molecule here that I missed. We're going to move this electron through these chains of proteins like this to the end. Okay, and as it moves and is passed between these molecules, these proteins here, its energy can be harvested because electrons have lots of energy. Now, why do we want to harvest that energy? Well, there are protons on both sides of this membrane. And protons are hydrogen ions, because if we get a hydrogen, it's got 1 proton and 1 electron. If we take the electron away, which makes it positive, it becomes just a proton by itself. That's why a hydrogen ion is called a proton. So there are protons on either side of the membrane. Now it turns out that the way that ATP synthase makes ATP is by protons flowing through it. So protons are going to flow through ATP synthase. Okay? And when that happens, ATP synthase can add a phosphate to ADP to make ATP. And that's what we want. We want ATP. Now, how would you get protons to move naturally through ATP synthase without any energy? Well, remember that molecules and ions as well move from a high to a low concentration. So if we have a higher concentration of protons on this side of the membrane compared to the other, protons will move through ATP synthase from high to low concentration of protons, okay, or hydrogen ions, it's the same thing, okay? So that's how we're going to make ATP. But how do we create this high concentration of protons up here? So to move molecules or ions from a low to a high concentration is like pushing a rock up a hill. It's active transport. You need energy. Where does that energy come from? It comes from our electrons here. So as these electrons move through these protein complexes, we're going to use their energy to pump protons from low to high. So basically against the concentration gradient. That creates this high concentration of protons on this side of the membrane, so then they can flow through ATP synthase, not requiring any energy, and ATP synthase can make ATP. So now we've dealt with this part here of the equation. We've still got oxygen and water to account for. Now remember, we're going to move this electron here. We're going to take this electron off the high energy electron carriers, and it's going to be dumped here at the end, and then it doesn't have anywhere to go, and we don't want electrons just floating around. They can damage our molecules and our cells. So what we're going to do is something really clever. We're going to put these electrons onto an oxygen molecule. Okay, we're actually going to put it on an oxygen atom. So what we're going to do is we're going to get oxygen, O2, and we're going to split that into what we call half O2, which is just one oxygen. And then we're going to add those electrons onto that oxygen molecule. But that creates a negatively charged oxygen, and we don't want that. So let's put some protons on at the same time, which is a hydrogen ion. What happens when we get oxygen and we add hydrogens to it? Well, we get H2O. So that is where our water comes from in our equation. And that is why we need oxygen. Oxygen is what we call a terminal electron acceptor. It accepts these electrons that are used, the energy is used, and then they're dumped out at the other end here, and they have nowhere to go. So we're going to stick them on oxygen. We're going to counteract the negative charge of the electron with some positive protons, which is a hydrogen. And so we're adding oxygens and hydrogens together, and we get water. So that is the whole process of cellular respiration. The first three steps, glycolysis, pyruvate oxidation, and the Krebs cycle, all create the high energy electron carriers, which are then used in the fourth step, the electron transport chain, which creates the vast majority of our ATP.